Hello everyone, my name is Zhou. Today I'm going to talk about the contributions of urban traffic to increase in road surface temperature, a case study in New York City. Cities are known to have concentrated energy use, which contribute a lot to the urban temperature growth. Among all the sources, traffic are believed to directly discharge heat into the surrounding environment and impact the road surface temperature. Although there are already studies concerning the estimation of road surface temperature increase using some models, they are very complicated to implement. So our goal here is to propose a simpler method for RST increase estimation with satellite-derived surface properties. We chose the city of New York to conduct our case study. The smallest research unit here is the census tract, and the New York City has a total of 2168 census tracts. And the research date is April 18th, 2017. It is a typical cloudless workday with relatively stable weather. And the data we used are the satellite data product from Landsat 8. Traffic counting data is called the Annual Average Daily Traffic (AADT), downloaded from the New York State Department of Transportation. The corresponding weather data are from the Automated Surface Observation System. For our methods, we first need a coefficient called the energy release coefficient, EV. It is derived from the net heat of combustion of gasoline, the fuel density, and the mean fuel economy. Reference values for these items can be found from relevant literatures. Then we need to define a control volume. We can imagine it as a box-like space based on the road surface, and the section area is defined as roadwise times the average vehicle height. The initial setting here is 30 meters for roadwise and 2 meters for the average vehicle height. The air temperature increase in one control volume due to vehicular waste heat can be understood that all the waste heat discharged by the passing vehicles will be totally used to heat up the surrounding air inside this control volume. This process can be represented by the equation here, where delta NC is the vehicle flux. It is the number of cars passing through this control volume, and RL is the total road length within this control volume. Delta T is the observation time, which can be cancelled on both sides. After calculating the air temperature increase, we want to convert it to the surface temperature growth, so we employ the surface energy balance model here to do a linearization in order to find out the form to calculate the change of surface temperature delta Ts. The initial surface energy balance equation is consisted of shortwave radiation, long-wave radiation, sensible heat flux, latent heat flux, and the ground heat flux. We then expand the whole surface energy balance equation and do a differentiation with respect to road surface temperature Ts. And finally, we get the equation to calculate the change of road surface temperature, delta Ts, as shown here. Two important parameters are the Fs and the Fa. We temporarily define them as energy redistribution factors. FS and FA are actually regulating the heat transfer process between air and land, as we notice that there is a linear relationship between delta Ts and delta Ta in our previous solution of delta Ts. This coefficient is just Fa over Fs. Fa and Fs can be calculated according to the two expressions here. Those intermediary parameters, such as air emissivity, surface emissivity, and the aerodynamic resistance, can be either calculated using the satellite product or the weather station data. Here are some results of our case study under the default setting with 30-meter roadwise. We could see that the pattern of road surface temperature increase is consistent with the traffic volume data pattern as shown before. The outer part of the city has much larger RST increase than the inner part of the city because the expressways near the boundary of the New York City have much larger traffic volumes than the inner city roads, especially at non-peak hours in residential areas. By the way, the energy distribution factors Fa and Fs are close in magnitude all over the city. The average road surface temperature is about 1.39 degrees C when the roadwise is 30 meters. We are wondering the performance of delta Ts when the roadwise is changing, because the roadwise is directly influencing the size of our control volume. So we perturbed the roadwise from 20 meters to 40 meters at a step of 5 meters. And we finally found that the average road surface temperature increase is changing from 2.09 to 1.05 degrees C. Another sensitivity analysis is conducted on the air temperature Ta, because air temperature is involved in the calculation of one of the energy redistribution factors, Fa. However, we have only one measurement site for the air temperature all over the New York City area, so we are wondering the influence of Ta on Fa. We perturbed the air temperature from 0 to 35 degrees C and find that the energy redistribution factor Fa is little influenced by the change of air temperature. So it means that the use of only one air temperature measurement is acceptable in our study. Our work can be summarized that we proposed a simple RST increase estimation method, and our results show that RST is increased by about 1.39 degrees C on average when the roadwise is set to be 30 meters. Second, we found that RST increase in our method is very sensitive to roadwise. Third, the change of air temperature has little influence on the RST increase in our method. And lastly, our method is limited by the availability and accuracy of traffic counting data. In addition, the precision of satellite-based retrieval of surface properties remains uncertain after rescaling processes.